Welcome to K-Means Clustering. This video covers the 6-step process in K-Means clustering algorithm, along with all the essential mathematical formulations underpinning the algorithm. Additionally, we should also see how to get optimal K and the time complexity of the algorithm. So to get it started, let's look at the goal of K-Means clustering, which is to partition the data into K clusters. So let's go through an illustration on the algorithm with a simplified data set. Let's assume we have been given a simplified data set of, in this case, 12 data points. First step is we've been given X, which is 12 data points, and K, which we have chosen to be 3. The X, which is the data set, is normalized so that it is unit-free. Such a normalization can be done either through a min-max transformation or through a z-score transformation or a similar method of your choice. Now coming back to K, K refers to the number of clusters in the data, and typically it's based on your knowledge on the data or a guesstimate based on your business experience. We shall learn later how to find optimal K for your data. The second step in this algorithm is assigning K-Centroids for your data points. For this data, we are showing the initialized centroids in red, green, and yellow. The initialization could be performed using one of the approaches, like Lloyd's algorithm, which is the original 1967 algorithm that completely assigns random initialization from your data. The other approach is a K-means ++ approach, which chooses centroids at random but weighted by the probability of choosing them based on the squared distance from the closest centroid. This also means that the data points which are far away from its current centroid have a higher probability of being chosen, and it assigns low probability to points that are already tightly bound with its centroids. The third step is to assign the data values to the centroids and thus form clusters. So each point is assigned to its closest center point or the centroid. In our particular case, the clusters are shown in green, red, and yellow. The next step, which is the fourth step, is we create new centroids as the mean values of all the samples assigned to the previous centroid. We have shown in this particular step that it is the dark green, the light red, and the orange as the new centroids. The next step, which is the fifth step, is where we calculate the errors for the centroid movement. It is calculated as the distance between the new centroid and the old centroid. We've shown it in blue arrows in the above picture. The next step, which also is the last step, is that we're going to check the convergence criteria, and if it has not been met, then the algorithm goes back to step number 3. But if the convergence criteria has been met, then the algorithm finishes and returns all the clusters formed. The open question is, what is the convergence criteria? There are 3 essential elements within the convergence criteria. The first one is that there is no reassignment of data point to different clusters, which means the clusters did not have any new entry or exit. The second element is there are no changes or minimum number of changes to the centroids, so that the centroids themselves have not moved or within a small tolerance level. The last and very important point is there is a minimum decrease in the sum of square errors. The sum of square errors is measuring the error between each data point and its respective centroid. So in this equation, xi is referring to the data point x in the ith cluster, and mu I is the centroid of the ith cluster. We have calculated a sum of squared difference between each data point and its centroid. But why should we use the sum of squared error and not any other measure? This is where we are going to look at some of the mathematical principles underlying the K-means clustering algorithm. Now let's see why sum of squared errors appear and what are the underlying mathematical assumptions. Let us say the data is from an equal weighted mixture of K spherical Gaussian densities, and that the Gaussians have the same variance, let's assume it's variance 1, but different means, mu1, mu2, mu3, so and so till mu k. The probability density function of such a mixture is given by a p of x function, which is 1 by square root of 2 pi into 1 by k times the sum of exponential powered x minus mu I. That is done for each of the k different mixtures that are within the density. Now, since the exponential function falls fast, this equation can be simplified and approximated as a 1 by square root of 2 pi k exponential of x minus mu of x the whole square, where the mu of x indicates the center nearest to x. Now that the approximate p of x has been formulated, let us go to the next step, which is we're going to see the likelihood of drawing sample points x1, x2, x3 till xn if the centers were actually mu1, mu2, mu3, so and so till mu k. Such a likelihood is approximated through this particular formulation, where we have multiplied p of x1 times p of x2 times p of xn till p of xn, and each of the p of x1 is the approximated p of x that we formulated earlier. This implies that there is a constant term to the left, which we are going to mark as c, and then a non-constant term in this particular approximation, which is nothing but the sum of squared errors. This implies that if we minimize the sum of squared errors to the cluster centers, then we can find the maximum likelihood mu1, mu2, mu k. And it is worth noting that the sum of squared distance is also called the Euclidean distance. This is why K-means by default is using Euclidean distance as its distance measure. It is also worth noting that if the data generating process had an exponential distribution, then our derivation would have been different, and we would be using a Manhattan distance instead of a Euclidean distance for the maximum likelihood solution. Okay? So now that we understood about the usage of the sum of squared errors, let's now look at how to choose an optimal K. The first and the most popular method is the elbow method. Here we look at the total error on the y-axis and different values of K on the x-axis. We look for the point where the error flattens out from its steep decline. So in our example, it so happens to be k equal to 2, and such a point is usually the optimal k. The second approach is to use cross-validation of your data to choose k. Depending on your cross-validation algorithm, for example, if you're using k-fold cross-validation, then you may validate to minimize errors while you're choosing the optimal k. The third approach is to rely upon a domain expert to look at your cluster formulations and validate if it is suitable for your business or not. The fourth approach is to use a sill-out score to get a good indication on your cluster formulation and then refine your k values. A sill-out score is calculated for each of your data point after the clustering is complete, and it is a ratio of similarity to dissimilarity measure. The similarity is denoted with an A of I, and that's denoting the distance between the data point and its own cluster, while the dissimilarity shown as B of I is the distance between the data point and its neighboring cluster. Okay, so generally sill-out score greater than 0.5 and closer to 1 indicates excellent separation between clusters and tightly bounded cluster points. Okay, now that we've looked at a few methods to choosing optimal k, before we finish this video, let's quickly understand the time complexity of the K-means algorithm. We are given n items, m dimensions, which is the m features, k clusters, which is what we want the clustering algorithm to do, and l iterations, which is chosen by the algorithm. Then the distance computation between two items is in the order of m. When we reassign clusters, it is in the order of k times n, and every iteration, a single iteration, is of an order of k times n times m. Now, to summarize, K-means is a popular partitioning algorithm that finds local optima, runs fast, works well on well-separated data set. Okay, so that's all for this video. Till next video, good luck to you and stay safe.